Good morning, students.
Good morning, ma'am.
Morning, ma'am.
Okay. All of you, please switch on your videos. Okay, then in our last class, we discussed about we are calculating the total resistance offered by the LCR combination. And we are called that total resistance offered by the LCR combination by a name. What's that, Achut? What is the total resistance offered by the LCR combination? The resultant resistance or the effective resistance offered by the series LCR combination is known by one name. What is that? Vidur?
Impedance.
It is known as impedance. And how we can represent impedance? Which letter is used to represent impedance? Anyone?
Sir,
Z.
Z. Z is used to represent the impedance of series LCR circuit. Impedance means the resistance, the total resistance offered by the inductor, capacitor, and resistor when it is connected in a series combination. Okay. And how we can calculate this impedance? Sania, what is the equation for calculate the impedance of a LCR circuit?
Root chi L minus chi C whole square plus R square.
Z is equal to root of chi L minus chi C the whole square plus R square, where R is the resistance offered by the resistor and chi L and chi C is the resistance offered by the inductor and the capacitor respectively. Is it clear? Okay. So here we are going to consider the phasor diagram once again. We are going to draw the phasor diagram with respect to current. So in the previous case, we are represent the phasor diagram with respect to voltage or EMF. Now we are going to consider the phasor diagram with respect to resistance, the resistance offered by all these three different components such as inductor, capacitor, and resistor. Okay, so once again, we are going to consider the phasor diagram with respect to resistance. Phasor diagram with respect to resistance. We know that the EMF produced by each component, that is in the case of resistor, VR is equal to I into R. Similarly, what about the EMF that is developed in an inductor, VL? If VR is equal to IR, what about the voltage or EMF developed across inductor?
I into chi L.
I into chi L. We just recall all these equations once again and we see EMF or the potential that is developed across the capacitor is given by VC is equal to I into chi C. So from all these three equations, it is very clear that the term I remains constant. The term current, the current through each component that is inductor, capacitor, and resistor are remains constant. Only the value of resistance is varies. In the case of the voltage that is developed in the case of VR, that is resistor, it is IR. The value of resistance is varies. It is R, chi L, and chi C respectively. So here we are going to draw a phasor diagram with respect to these three components, that is inductor, capacitor, and resistor. So first of all, a horizontal line which represents the phasor diagram corresponding to the component resistor. Okay, since the current remains a constant, we are not considering the I value here. We are only take the value of resistance offered by the resistor, that is R. We know that normally in the phasor diagram with respect to voltage, we are taking VR here, the voltage across the inductor here, and voltage across the capacitor here, VC. So here we are going to represent the phasor diagram with respect to resistance. The resistance offered by the resistor is taken by R. And here we take VL minus VC, VL minus VC. And we know that VL minus VC is equal to I chi L minus I chi C. Or here the term current is constant, we can take outside. It becomes I into chi L minus chi C. Since the term current is a constant, here we are not take that value. So instead of VL minus VC, here now we have chi L minus chi C. And what about the resultant? If this chi L minus chi C and R is represent the two adjacent side, then the resultant is represent in this direction. The resultant resistance or the total resistance is represented by Z. Z is equal to root of chi L minus chi C the whole square plus R square. So this is the phasor diagram with respect to resistance. R is taken along the horizontal axis. Chi L minus chi C, that is the resistance offered by the combined effect of the inductor and the capacitor. It is taken along the y-axis or vertical axis. So this line represents the diagonal. According to parallelogram law, we can say that the diagonal that is originated from the same point represent the resultant resistance offered by the LCR combination. That is what is we are call it as impedance of the circuit. Z is equal to root of XL minus XC, not chi L minus chi C the whole square plus R square.
Ma'am,
Yes.
can you say how that became chi L minus chi C?
Chi L minus chi C, because we know that in the case of voltage offered by the inductor and capacitor in the phasor diagram, in the previous case, I will show it once again. The phasor diagram with respect to EMF. Here we have VR, here it is VL, and here it is VC. And we consider a condition if the EMF offered by the inductor is greater than EMF offered by the capacitor. Suppose if VL is greater than VC, then VL minus VC is taken along the direction of VL. So here in the previous case, we take the VL minus VC here. VL minus VC along the direction of VL. And we know that what you mean by VL? VL is given by I into chi L. VC is equal to I into chi C. Then VL minus VC is equal to I into chi L minus chi C. But here the term current remains constant. That is why we taken only R along the horizontal axis. Similarly, we didn't consider the case of current. It remains a constant value. And here we represent the phasor diagram with respect to resistance only. So here we don't need to consider the value of current here. So instead of this VL minus VC, here we take chi L minus chi C. Is it clear?
Yes, ma'am.
Okay, and in the previous case, the resultant voltage, if the phasor diagram is with respect to voltage or EMF, the resultant is represented along this direction, but along the resultant direction, we are portrayed the value of voltage. That is the resultant voltage V is equal to, what is the value of resultant voltage in that case? Root of VL minus VC the whole square plus the voltage offered by the resistor, that is VR square. So this is the phasor diagram with respect to EMF. But here now we are drawing the phasor diagram with respect to resistance. So the R is taken along the horizontal axis. chi L minus chi C along the vertical axis. So the resultant is given by this direction. Here we consider the LCR combination. So here we need to consider the resistance offered by each components. So it becomes impedance. Instead of the term resistance, here we are using impedance represented by the letter Z. Z is equal to root of chi L minus chi C the whole square plus R square. Is it clear now? Okay.
Yes, ma'am.
Now we are drawing a line, or here we don't know how much angle this value of resistance is deviated from that of the total value of resistance. We don't have any idea about how much angle this value of resistance is deviated from the total value or the resultant value of the resistance. So suppose we are consider this angle. Suppose we just imagine that this value of resistance is deviated at an angle of phi away from that of the total resistance offered by this LCR combination. Here we have the resistance offered by the resistor. It is taken by R. And we don't have any idea how much angle this resistor with resistance value R is deviated from the total resistance offered by the LCR combination. So here we just imagine or suppose we take that angle as phi. Here we want to find out an expression for power factor. We want to calculate an expression for power factor, and also we want to calculate the direction of the current. So here we are going to make some changes into this phasor diagram with respect to the resistance. So that is what is the main aim that we are using the phasor diagram method in an LCR combination. Here we have two methods are possible. One is phasor diagram method and other is analytical method, in order to derive an expression for current and also to find out the direction of the current that is flowing through the LCR combinations and all. And also we want to calculate the value of power from this LCR combination. So here we are using this phasor diagram method, and we are starting with phasor diagram with respect to resistance. Here R is taken along the x-axis and chi L minus chi C is taken along the y-axis. Now we imagine that here we don't have any idea about how much the value of resistance is varied from that of the total resistance of the LCR combination. So we just imagine that this resistance, the value of resistance is varied by an angle of phi away from that of the total resistance. And we draw a line that is parallel to chi L minus chi C. Draw another line parallel to chi L minus chi C. So here we consider two cases. One is we take an angle, and that is an angle that is deviated from Z. So it is an angle between the value of resistance and that of the total resistance offered by the LCR combination. We don't have any idea about that angle. So suppose we just take that or assume that angle as phi. Okay. The second consideration that we are taken here, we draw a line parallel to chi L minus chi C to this horizontal axis. We draw a line chi L minus chi C. We draw a line parallel to chi L minus chi C to this horizontal line. Then students, can you guess what about the measurement of this parallel line? What about its value? It is also equivalent to chi L minus chi C, right? Because here we consider, here we draw a line parallel to chi L minus chi C. So we can say that that side is also equivalent to chi L minus chi C. Okay. So here we get a triangle with the sides R, chi L minus chi C. It's the altitude, and hypotenuse is equal to, Z is equal to root of chi L minus chi C the whole square plus R square. Okay. Here we get a triangle with a base is with a resistance R, altitude with another resistance chi L minus chi C, and the hypotenuse with the total resistance of the LCR combination Z is equal to root of chi L minus chi C the whole square plus R square. This triangle is known as impedance triangle. So here we get a triangle. That triangle is known as impedance triangle. Impedance triangle, or normally you can call it as impedance diagram, or it is impedance triangle. The Phasor diagram with respect to resistance is also known as impedance diagram. And here by taking all these consideration, we get a triangle. We call that triangle as impedance triangle. Why it is known as an impedance triangle? Because it represents a triangle and its all sides are represents the value of resistances. If we are consider the any sides of this triangle, it represents a value of resistance. The base is represented by the resistance R, altitude by the resistance chi L minus chi C, and the hypotenuse is represents the total resistance offered by this LCR combination. So if we are consider any side of the triangle, all the sides are marked with resistance. That is why this triangle is known as impedance triangle.
Ma'am,
Yes.
can you tell the reason again one more time?
Okay, Gauri. So here we get a triangle. Okay. The base is represented by a value R. What do you mean by R? R is the resistance offered by resistor. Similarly, we are consider the altitude or the height of the triangle. It is represented by another side. What is the value of that side? Chi L minus chi C. It is another value of resistance offered by inductor and capacitor. Again, we are consider the hypotenuse of the same triangle. What about it is represents? It represents the total resistance. Here Z is also represents the resistance. It is, even though it is impedance, impedance is nothing. It is the resistance offered by the LCR combination. So when we are considering this triangle, suppose if we are giving it is name OBC, but it is represent all the three sides of the triangle is represents a resistance value. Since it is represents a resistance value, we can call it as an impedance triangle. Impedance means resistance, the total resistance of the combination. Since all the sides of the triangle is represents a resistance value, we can call this triangle as impedance triangle. From this diagram, we need to derive two important equations. That's why we are consider the Phasor diagram with respect to resistance. That's all. So this triangle is known as impedance triangle because all the three sides are represents the value of resistance. That's why we call this triangle as impedance triangle. Okay. Now, what is the use of this impedance triangle? Impedance triangle is actually used to find out the direction of the current that is flowing through LCR combination. Impedance triangle is used to find out the direction of current that flows through LCR, series LCR combination. Impedance triangle is used to find out or determine the direction of current that flows through series LCR combination.
Once more.
Okay. Impedance triangle is used to find out the direction of the current. Impedance triangle is used to find out the direction of current that flows through series LCR combination. Here we are consider the series LCR combination, inductor, capacitor and resistor that connected in series. So we want to find out the direction of the current that is flowing through this series LCR combination. So using this impedance triangle, we can find out the direction of the current that flows through series LCR combination. Okay. So for that, here we consider tan phi. From impedance triangle, we are calculating or we are going to determine the direction of current. From impedance triangle, we can determine the direction of current. For that, we consider the angle tan phi. Normally, the tan angle we are used to find out the direction of any physical quantity. Similarly, here we are used to find out the direction of current. For that, we are consider tan phi. What is the equation for calculating tan theta or tan phi? General equation in trigonometry. Opposite side divided by
Adjacent.
adjacent side. Opposite side divided by adjacent side. This is the general equation for calculating tan phi. Normally, the tan angle is used to find out the direction of any physical quantities in physics. So similarly, here we want to find out the direction of current. So for that, we consider tan angle. So here the angle is phi. We assume an angle between the resistance and that of the impedance, that is phi. So here we have tan phi is equal to opposite side. What is the opposite side here in this triangle?
Chi L minus K.
Chi L minus chi C. And what about the adjacent side?
R.
R. So tan phi is opposite side divided by adjacent side. Here from the figure it is very clear that the opposite side is given by chi L minus chi C divided by adjacent side is given by the resistance R. So we get tan phi is equal to chi L minus chi C divided by R. From that we can say phi is equal to if tan phi is equal to chi L minus chi C divided by R, which implies phi is equal to, how we can find out the phi? Take the tan to RHS. It becomes
Tan inverse.
very good. Tan inverse. Tan inverse chi L minus chi C divided by R. So if you know the value of chi L, chi C and the resistance R, then you can easily find out this angle phi. Thereby you can see how much angle the current is deviated. So the direction of the current is given by the equation tan phi is equal to chi L minus chi C divided by R, or we can write phi is equal to tan inverse chi L minus chi C divided by R. Again, one more equation that we are used to derive here from the same triangle, that is power factor. So write a next subheading, power factor. There is no derivation steps and all. You only need to study the equation. There say nothing about the power factor from this topic. So just understand that power factor from this impedance diagram. Actually, this is the power factor of LCR circuit. So power factor of LCR circuit from impedance diagram. power factor of LCR circuit from impedance diagram. Power factor is given by another angle. That equation is important. Cos phi. Cos phi. What is the equation for calculating cos phi? Cos theta.
Adjacent side by hypotenuse.
Adjacent side divided by hypotenuse. Cos phi is equal to adjacent side divided by hypotenuse. Then power factor. Cos phi is equal to adjacent side. What is the adjacent side from this figure? Adjacent side.
R.
R. R is the adjacent side. And what is our hypotenuse? Z. So the power factor cos phi is given by adjacent side is R divided by hypotenuse is Z. So cos phi is equal to R by Z. So in your numerical problem, sometimes you may be asked to calculate the power factor of LCR circuit, and they provide the value of this R and Z, the resistance offered by the resistor, and the impedance of the circuit is given. Then you can easily calculate the power factor using this equation. Cos phi is equal to R by Z, such that phi is equal to cos inverse R by Z. So this is the general equation for calculating the power factor. That is cos phi is equal to R by Z. There is no particular any kind of definitions and all for this power factor. This is a general equation for calculating the power factor of series LCR combination. So from the same impedance diagram, we can calculate the direction of the current. That is tan phi is equal to chi L minus chi C divided by R. Similarly, here from the same impedance diagram, we can calculate the power factor of this series LCR combination. It is given by a general expression cos phi is equal to R by Z. Okay, all these equations are important regarding with the numericals. There are a lot of problems are there regarding with this tan phi, cos phi, power factor, and about the value of EMF and all. So after completing this lesson, we can practice some problems from the exercise sessions during revision time. Okay. So that's all about the series LCR combination by Phasor diagram method. And one more method is there, that is analytical method. Even though we are using the Phasor diagram method and that of the analytical method, we are get the same equation for calculating the direction of the current and also for the power factor. The equations will be the same. Okay, so I am trying to skip that analytical method. Only any one of these two methods are important. You can use either Phasor diagram method or analytical method. Normally, the analytical methods are not followed in schools. Okay, so if we get the time, we can follow this. We can practice this analytical method also, because it is a huge steps of derivations are there in the analytical method. So here we are skip the analytical method. We are only follow this Phasor diagram method. Only our aim is to derive an expression for determining the direction of the current. That is, here we are deriving tan phi. Tan phi is equal to chi L minus chi C divided by R, or phi is equal to tan inverse chi L minus chi C divided by R. And equation for power factor. Power factor is given by cos phi is equal to R by Z. These two equations are very, very important from this series LCR combination. Is it clear? Only about the power factor and that of the direction of the current tan phi. Can we move to the next topic? So here I am just skip the analytical method. Whenever we get the time, we can also derive these steps. Actually, it is not at all important because we are deriving the same equations from this analytical method. Both are same. Phasor diagram method and analytical method. From these two methods, we are deriving the same equations for power factor and that of the determination of angle or the equations for finding the angle direction of the current, that is tan phi. So now we are going to the next topic, that is resonance. Resonance. Okay, so in order to explain this term or the resonance, once again we need to recall the equation for impedance. What do you mean by impedance? Emmanuel, what do you mean by impedance?
It's a kind of resistance.
It is not a kind of resistance, it is the total resistance. The total resistance offered by the series combination of LCR circuit is known as impedance. And what is the equation for calculating impedance? Z is equal to, anyone? Z is equal to? Equation for calculating impedance is chi L minus chi C the whole square plus R square. So this we are starting the resonance, again recalling the term impedance. Impedance means the total resistance offered by the LCR circuit in a series combination. The equation for calculating the impedance is Z is equal to root of chi L minus chi C the whole square plus R square. Okay. Now you just imagine that if chi L is equal to chi C, that is the resistance offered by the inductor becomes equal to the resistance offered by the capacitor. If chi L is equal to chi C, then what is chi L minus chi C?
0.
It is equal to 0. Because if chi L is equal to chi C, we can say chi L minus chi C is equal to 0. So this term becomes equal to 0. So according to impedance, we know that Z is equal to root of chi L minus chi C, the whole square plus R square. But whenever the resistance offered by the inductor is equivalent to that of the resistance offered by the capacitor, chi L is equal to chi C, we can say chi L minus chi C is equal to 0. Then what about the equation for impedance becomes Z is equal to root of R square. The first term cancels, or we can say Z is equal to R. The LCR circuit becomes purely resistive in nature. This condition is known as resonance condition of LCR circuit. Okay, so what is the resonance condition of an LCR circuit? We are starting with the impedance, the total resistance offered by the LCR circuit. The total resistance offered by the LCR circuit is given by Z is equal to root of chi L minus chi C the whole square plus R square. But whenever the resistance offered by the inductor and the capacitor becomes equal, by adjusting some kind of frequency between the inductor and capacitor, we can make this chi L equivalent to that of the chi C. So when chi L is equal to chi C, we can say that chi L minus chi C is equal to 0. Then the equation for impedance becomes Z is equal to, this entire term becomes equivalent to 0. So Z is equal to root of R square, or Z is equal to R. This condition is known as resonance condition. So what is the resonance condition? Resonance condition means if the capacitance, the resistance offered by the inductor and that of the capacitor is equal in an LCR circuit which is connected in series, then the circuit is purely behaves like a resistive circuit. Okay. So resonance condition. What do you mean by resonance condition? If the resistance offered by the inductor and capacitor becomes equal, if the resistance offered by the inductor and capacitor becomes equal, then the term chi L minus chi C is equal to 0. Then the term chi L minus chi C is equal to 0. Under this condition, the series LCR circuit, under this condition, the series LCR circuit behaves like a purely resistive circuit, because here the resistance offered by the resistor is only present. The other term is cancelled. So under this condition, the circuit is behaves like a purely resistive circuit. This condition is known as resonance condition. This condition is known as resonance condition. So if the resistance offered by the inductor and capacitor becomes equal, that is chi L is equal to chi C, the term chi L minus chi C is equal to 0, then the circuit is behaves like purely resistive circuit, that it is becomes equal to Z is equal to root of R square. The first term completely equivalent to 0. So we can say Z is equal to R. Now the resistance is completely behaves like a purely resistive circuit. Here the resistance offered by the resistor is only present in such cases or in such condition. This condition is known as resonance condition. Okay, so whenever we are while practicing the problems, when I am asking what is the resonance condition, you just answer that chi L is equal to chi C. Chi L is equal to chi C is known as actually the resonance condition. So under such condition, we can say Z is equal to R. So here Z is equal to root of R square, or we can say in such cases, the circuit is purely behaves like a resistive circuit. Z is equal to R. This is the resonance condition. Z is equal to R. Then chi L is equal to chi C. Then under resonance condition, what is the value of EMF and that of the current? What about the nature of EMF and the current? Does they are in same phase or in different phase? Under resonance condition, what about the nature of current and EMF? Think and answer. Under resonance condition, the circuit is purely behaves like a resistive circuit. It behaves like a purely resistive circuit. So what about the nature of current and EMF developed in the LCR circuit?
Same phase.
They are in same phase, because whenever the AC voltage is passing through resistor, we derive two equations for current and voltage. The voltage is given by V is equal to Vm sin omega t, and the current I is equal to Im sin omega t. This is what is we are starting in the very beginning of the class. The expression for EMF and current for a resistor, if the circuit is only contains the resistor. So here under the resonance condition, the circuit is purely behaves like a resistive circuit. The inductor term and conductor term, capacitor term is not present here because chi L is equal to chi C, chi L minus chi C becomes equal to 0. So our LCR circuit now becomes purely behaves like a resistive circuit. So it satisfies the conditions and equations for that of the AC voltage through resistor. So under resonance condition, we can say one more characteristics. Under resonance condition, the EMF and the current are in same phase. Both the current and voltage or EMF are in same phase. Is this idea is clear to you? Why? Because they are in same phase, because under resonance condition, only the resistance offered by the resistor is present. All the other two terms gets cancelled. Chi L minus chi C becomes equivalent to 0. So our LCR circuit behaves like a purely resistive circuit, and here the total resistance, that is the impedance of the circuit, is only due to the presence of the component resistor in the circuit. And in the case of a resistor, we know that the voltage and the current, they are in same phase. V is equal to Vm sin omega t and I is equal to Im sin omega t. Okay, now it's the time. That's all for today.